In our last video, we talked all about hash maps. We looked at how they let us save data as key value pairs. So we can look things up instantly without having to loop through our data over and over again. It is an amazing tool, but it comes with a trade off memory. When you use a hash map, you are purposely using up more RAM just to save your CPU from doing extra work. But what happens when you don't have that extra memory to spare? Say you're working on a mobile app or a device with strict memory limits, and your dataset is huge. If you try to copy all that data into a hash map, your application might run out of memory and crash. This is where we need a different approach. Today, we are diving into two pointers pattern. Instead of using extra memory to solve our problems, we are just going to change how we move through our data. We use two variables, which we call pointers, to keep track of indices in a string or an array, and we move them across the data at the same time. This simple trick lets us completely avoid nested loops, turning a slow program into a fast linear scan without using a single byte of extra RAM. Now, again, this isn't just an abstract concept for coding interviews. It is something engineers use in real life production software every day. Think about a text editor or a compiler that needs to check if a piece of text is symmetrical, like making sure brackets match or checking if a word is a palindrome. If the program uses a nested loop, it will have to start at the beginning of the text and scan forward again and again for every single character. That would make the app lag. Instead, developers use two pointers. One starts at the very beginning of the text, the other starts at the very end. And they just walk inward towards the center together, checking if the characters match. You also see this in digital media and video streaming players. When a video engine needs to find specific timestamp frames or adjust a timeline marker within a huge list of data, running a nested loop would cause the video to stutter or drop frames. By using parallel pointers to adjust the boundaries from both ends, platforms like YouTube can process playback timelines smoothly. So, how do you spot a situation where you should use this? As always, look out for trigger words in your requirements. Whenever you see phrases like sorted array, finding a pair, palindrome, or dealing with a container, that is your cue. The main rule to remember here is simple. Always move the pointer that actually has a chance at improving your current result. Pointers do not always have to move inwards, okay? Depending on the structure of the data, the problem you're trying to solve, pointers can move in completely different direction. Like the one we just looked at, inwards. You place a pointer at the start, one at the end, and they just walk towards each other. This is the ultimate choice for checking symmetry. Another direction you can consider is forward. In this variation, both pointers start at the beginning of the data structures and race forward in the same direction but at different speeds or intervals. For example, if you need to merge two sorted lists together or remove duplicates from a list without copying it, you keep a slow pointer to track where the clean data goes and a fast pointer to scan ahead looking for the next unique item. But sometimes the most efficient path is to do the exact opposite of the palindrome check. You place both pointers right next to each other in the dead center of your data and you push them outwards towards the edges. Now see, no matter which direction your pointers are traveling, inward, forward, or outward, the core philosophy remains identical. You are using numerical values to guide a single loop across the data without duplicating your data structure in memory. Let us look at an example to see exactly how this saves our program from doing unnecessary work. Imagine you need to write a function that checks if a string is a palindrome. This means it reads exactly the same forwards and backwards like the word radar. If you were to solve this using a classic beginner approach that consumes memory, you might try to reverse the entire string first, save the new reverse string into a variable, and then see if the old string matches the new one. This works fine for a tiny word, but if your program is validating massive log files, full DNS sequences, or an entire text document containing millions of characters, by splitting the text and reversing it, you are duplicating the entire massive string in the computer's RAM. If the device runs low on memory, it will throw an out of memory exception and crash. Let us look at how cleanly we can solve this using the two pointer strategy instead, without copying a single thing. Suppose we pass the text radar in a function. When the function first starts, it sets up our two tracking variables, left pointer and right pointer. Here is exactly how the loop squeezes inwards. When the left pointer is at index 0, the right pointer is at index 4. It checks if the R is different from R. No, they match perfectly. So we move both the pointers inward. That is, left pointer becomes 1 and right pointers becomes 3. Now, left pointer is at index 1, that is A, and right pointer is at index 3, that is A again. And we check that again and they match too. So move them inwards. Left pointer becomes 2, right pointer becomes 2. And they are both the same again. So the loop stops cleanly and the function returns true. Notice why this is a complete win in the memory. No matter if the text file is 5 characters long or 5 million characters long, we never duplicate the text. We never split it into an array, and we never build a reverse string copy. The only extra memory we allocate are those small variables tracking index positions. They take a microscopic fixed amount of memory that never grows. Because its memory footprint stays completely flat, regardless of how massive the text gets, your code will run seamlessly on the lowest end hardware without any threat of a memory crash. Once you learn how to guide your code using index movements like this, writing fast programs stops being a guesswork. It is just about choosing the right strategy for the data you have. Now we have covered hash maps and two pointers. We have a really great foundation. In our next video, we are going to build on this and look at the sliding window pattern, which helps us track subsections of an array. Just a view. As always, the resources I used are linked down in the description below. If this helps you understand the pattern a bit better, feel free to subscribe and I'll see you in the next one.